Down here on Earth, movement comes with a steep price. If you want to push a 300,000-pound airplane through the thick soup of our atmosphere, you need massive engines burning thousands of gallons of fuel just to fight the relentless drag of air resistance. The same rule applies on the ground. To keep a car moving at highway speeds, you have to keep your foot steadily on the gas pedal. The moment you stop feeding it energy, the friction of the road and the surrounding air will rapidly drag you to a dead stop. But if you step off our planet and out into the void, the rules completely flip. In space, you don't need engines or burning fuel to maintain your speed. Objects just coast, silently and endlessly. Look at the International Space Station. It's roughly the size of a football field, weighs nearly 1 million pounds, and floats high above the Earth at thousands of kilometers per hour without constantly firing any thrusters.
To understand how our solar system actually works, we have to unlearn our terrestrial instincts. Out here, moving is the default state of reality. It's stopping that's the hard part. The reason space behaves this way is because it is a vacuum. Unlike Earth, there is no atmosphere. There is no gas or suspended particles to create drag, rub against a moving object, and steal its kinetic energy. Look at the Juno space probe. Traveling through a vacuum, it avoids the physical resistance that grounds our airplanes. Unburdened by friction, Juno reached a staggering 266,000 kilometers per hour, a velocity that would instantly burn up any craft in Earth's atmosphere. But this introduces a massive problem. If there's exactly zero friction to slow things down, then the laws of momentum dictate that any moving object, whether it's a tiny human-made probe or a giant planet, should just keep flying in a perfectly straight line forever into deep space.
Since our planet isn't currently hurtling off into the freezing depths of the galaxy, there has to be an enormous, invisible force out there actively wrestling with that momentum and steering our path. That tether is the Sun. It holds so much mass, 330,000 times more than Earth, that its gravity acts as an anchor for the entire solar neighborhood. To put that in perspective, the strength of gravity on Earth is about 10 newtons per kilogram. On the surface of the Sun, that pulling force is 270 newtons per kilogram, a crushing 27 times stronger. This diagram shows how gravity interacts with a moving planet. The red arrow represents momentum, attempting a straight line. The blue arrow shows the Sun's gravity pulling it inward, creating a circular orbit. But this leash isn't infinite. Gravity weakens further out in space. So how do all these planets, resting at wildly different distances, avoid either plunging into the burning star or drifting away into the dark? This chart shows the average orbital speeds of the planets, and it reveals the exact balancing act keeping us alive. Planets in the inner solar system feel an intense gravitational pull, so they travel extremely fast. Mercury, the closest planet, screams around the Sun at a blistering 48 kilometers per second. But as we move outward, the Sun's grip loosens, and the required speed plummets. By Jupiter, the speed drops to just 13 kilometers per second, cascading steadily downward the further out we go. A planet's speed isn't a random coincidence. It is a strict mathematical requirement, perfectly tuned to balance against the strength of gravity at that exact distance. Because space is an empty vacuum, completely stripped of chaotic variables like friction or wind resistance, gravity gets to act as the undisputed, solitary master of the solar system. Without anything to slow them down, these massive bodies orbit with mathematical precision, ticking around the Sun like a giant watch. We know exactly how precise this cosmic clockwork is because of a strange mystery involving the orbit of Uranus in the 1800s. In 1821, astronomers carefully tracked Uranus and realized its movement was contradicting the strict rules of the Sun's gravity. It was speeding up and slowing down at the wrong times. Rather than assume the laws of physics were broken, scientists deduced that a massive, unseen object must be lurking further out in the dark, tugging on Uranus with its own gravity. By running the math backward, they predicted the exact location of a brand new planet, Neptune, before any human eye had ever observed it through a telescope. When you strip away the friction of our world, space is no longer a chaotic void. It reveals itself as a highly ordered, beautifully readable system governed entirely by the silent pull of gravity.